Today's webinar is part of the Waterwork Water Management in Container Nursery series, and today we'll be looking at operating and scheduling irrigation systems. In today's session we'll learn about plant water use, the link between nutrient and water management, how plant water use varies in different nursery environments, how water is held in growing media, how to schedule irrigation systems to match plant water use, how to measure plant water use, and how to measure leachate volumes. Water needs vary for different plants and at different stages of production. Many nurseries just water to keep the plants alive. However, this often means that the plant with the highest water use or most frequent demand dictates how the whole nursery is irrigated. Many nurseries apply the same amount of water all summer and might reduce the rate in winter, even though water requirements can vary by up to 300% on a daily basis. In winter, many plants in low light conditions can go several days without irrigation. The end results of this situation are excessive use of water, excessive leaching of nutrients, uneven and slow plant growth, leaf drop, poor internode spacing and plant shape, excessive drainage, and elevated or contaminated water tables. All of these will affect the nursery's profitability. All metabolic processes performed by plants depend on water. Nutrients taken up by the roots are moved to the tops in a stream of water powered by evaporation. Nutrients are absorbed mainly from water held in the growing medium. Plant growth depends on the management of nutrients, and the supply of nutrients to the plants depends on the management of water in the nursery. Consequently, nutrients and water are interrelated. Water is also used for cooling of plants. The whole system is driven by transpiration at one end and available water at the other. Transpiration is the process where water is changed to water vapor in the plant and then lost to the atmosphere through small openings in the plant leaf called stomata, which also control the amount of water vapor exchanged with the atmosphere. One function of this mechanism is to cool the plant. If there's not enough water available, or it becomes too hard to extract from the growing medium, then the stomata will close. If the stomata close, then the metabolic process starts to close down as well, and the plant stops growing, as well as reducing or stopping the transfer of water from the plant to the atmosphere. As plants transpire most of their water for cooling, the plant becomes overheated and starts to wilt, and every time this happens, it affects the bottom line. Most nurseries have a range of growing environments. Plants in the open, exposed to full sunlight and wind, will use more water than plants under shade cloth where the solar radiation, temperature and wind are reduced. Plants in poly or glass houses can experience higher temperatures and humidity but still have reduced radiation and wind, and will generally use less water than outside in summer, but this situation could be reversed in winter. Evapotranspiration is the sum of the evaporation from the growing media surface and transpiration from the plant. Evapotranspiration varies on a daily basis and is driven by 4 environmental factors: solar radiation, temperature, humidity and wind. Solar radiation is the largest energy source and is able to change large quantities of liquid water into water vapor. The potential radiation is dependent on the position of the sun at different latitudes and seasons. The actual radiation that reaches the plant surface depends on how clear the atmosphere is and the presence of clouds, which reflect and absorb major parts of the solar radiation. Air temperature is increased by the heat emitted by the earth that has absorbed the solar radiation. In sunny, warm weather, the loss of water by transpiration is greater than in cloudy and cool weather. The energy from the sun and surrounding air is the main driving force behind the vaporization of water. The difference between the humidity within the leaf and the surrounding air is the determining factor for how much water is lost from the plant. The higher the humidity, the lower the transpiration rate. The process of water vapour removal depends to a large extent on wind and air turbulence, which transfers large quantities of water over the crop surface. When plants are transpiring, the air above the plants becomes gradually saturated with water vapour. If this air is not continuously replaced with drier air, then the transpiration rate decreases. For humid conditions, the wind can only replace saturated air with slightly less saturated air, and consequently for a given wind speed, high humidity will affect evapotranspiration far less than a hot, dry wind. Different plants will use different amounts of water. Generally, water use will be less from plants with small, narrow and sparse leaves than from those with large, broad and numerous leaves. The difference could be as much as threefold. The stage of growth and the size of plant will dictate how frequently it needs to be irrigated. Plugs that have just been transplanted and seedling trays will require frequent small amounts of water. The roots can only draw water from a small volume of growing media, and evaporation from the top of the container is significant. Smaller droplet sizes from overhead irrigation are better to minimise plant damage and media splash. Plants at the next stage of growth will require moderate amounts of water, but no more than daily. The canopy generally shades the top of the container, reducing surface evaporation, and the roots can generally explore the whole of the growing media volume to draw down the maximum amount of water before needing to be irrigated. Plants that have large canopies and are almost root bound will require larger amounts of water more frequently, as the storage volume of the extensive root system displaces the growing media and reduces the potential stored water volume even in large containers. The storage volume in most containers is now significantly underbalanced to the plant canopy volume, and water may now need to be applied more than once a day. Water is held by surface tension in the small pores or micropores of the growing medium. The water held in the larger pores or macropores generally drains out, providing the air porosity of the growing media. The smaller pores are referred to as capillary pores and will move water into the growing media under bottom watering systems. The larger pores, filled with air, are called non-capillary pores and are responsible for the air-filled porosity of the growing medium. In containers, after drainage has stopped, the media at the very bottom of the container remains saturated, with the moisture level gradually decreasing to be the least at the top of the growing media surface. The amount of water held will depend on the pore sizes in the growing media and the air-filled porosity. The higher the air-filled porosity percentage, the lower will be the water holding capacity. Readily available water is mainly held in pores between 0.1 and 0.25 of a millimetre. Water held in finer pores is generally unavailable to plants as it is held too tightly. Pores of larger size tend to increase the amount of air in the growing media. Irrigation scheduling is the process of applying the right amount of water at the right time. The first step in determining irrigation schedules is to understand how the irrigation system is applying water, how quickly and how uniformly. Then the amount of water the plant is using has to be determined. From this information, the length of time and how often the system needs to be run can be calculated. Finally, the outcome of the irrigation event needs to be monitored to find out how effective it's been. The first step in the process is to measure the irrigation system performance and to calculate the mean application rate and scheduling coefficient. The next step is to calculate or measure plant water use by using evapotranspiration or weight. From this information, the runtime can then be calculated. The system is run for the calculated time, and the water that flows from the bottom of the container, or the leachate, is collected. Alternatively, the plants can be weighed to measure how effective the irrigation has been. The leachate volume or container weight can then be used to fine-tune the irrigation scheduling. The first step in this process is to perform a catch can test to determine the mean application rate and scheduling coefficient of the system. Set out catch cans over an appropriate grid to include parts of the area, including corners where plants would normally be placed. Place weights such as gravel in catch cans to stop them blowing over. and also remove any plants that will interfere with the flow of water from the sprinklers into the catch cans. Then draw a sketch of the layout. Turn on the sprinklers and note the time, then run the system for the time it would normally operate for. When the sprinklers are turned off, note the time and check that no sprinklers drain into the catch cans, and then calculate the run time. Measure and record the amount of water in each catch can, then calculate the results using the Waterwork calculator or the catch can test data collection and report calculator, which can be downloaded using these website links. Here is a video showing how to do the catch can test that's been described.
The benefits in doing this, in doing the whole exercise, is where we were able to find out exactly what our irrigation system is doing, and going forward now we know we get very even watering. So we've been quite impressed with the process and highly recommend it.
An efficient irrigation system operating to industry best practice provides you, as a grower, with an opportunity to obtain real operational and economic benefits. The key function of an efficient irrigation system is to apply the appropriate volume of water evenly to meet all plant needs in the time available. An efficient and effective irrigation system should apply water evenly across the cropping area, apply the correct volume of water, often enough to meet plant demands, and apply the required water in the time available. An overhead irrigation system set up to industry best practice, incorporating an appropriate design and layout, coupled with a complete maintenance program, can meet these goals. The performance of an overhead irrigation system can easily be evaluated by a grower conducting a simple catch can assessment. To do this, we need to understand the measurement parameters that are used. An efficient overhead irrigation system should apply the water at the appropriate application rate. To take full advantage of the water holding capacity of your growing media, the mean application rate, or MAR, should be less than the absorption rate of your growing media. Application rates of between 10 mm per hour and 25 mm per hour are considered suitable depending on your growing media components. Some growing media absorption rate examples are a growing media consisting of 85% bark and 15% sand would have an absorption rate of approximately 10 mm per hour. A growing media consisting of 85% bark, 15% sand, plus a wetting agent would have an absorption rate of approximately 15 mm per hour. A growing media consisting of 75% bark, 15% sand, and 10% coir would have an absorption rate of approximately 20 mm per hour. A growing media consisting of 100% coir would have an absorption rate of approximately 25 mm per hour. Secondly, an irrigation system should apply water evenly across the crop. The coefficient of uniformity, or CU, measures how evenly water application is distributed over the irrigated area. The CU takes both wet and dry areas into account and relates these to the average application. The CU is measured as a percentage, with 100% being the absolute ideal. A minimum value for fixed overhead systems is a CU of 85%. New system designs are expected to operate with a CU of 90% or better. Thirdly, the system should apply water to the whole area, minimising dry spots over the same time frame. Scheduling coefficient, or SC, is a measure of the extra time required to irrigate an area to ensure the driest section receives the required amount of water. The scheduling coefficient, or SC, is expressed as a number greater than 1, with 1 being the ideal. A good scheduling coefficient, or SC, is 1.2, with an upper limit of 1.5. The SC can also be used to calculate how long the irrigation system needs to operate. For example, if it takes 10 minutes to wet up the average container in an irrigation zone and the SC is 1.5, it will take 1.5 times 10 minutes, or 15 minutes, to wet the driest container. Therefore, a container receiving the appropriate amount of water within the 10 minutes now receives an extra 50%, while the driest container is brought to capacity. To do a catch can assessment of an overhead sprinkler system, it is first necessary to gather some information about the sprinklers used. Sprinklers are designed by their manufacturers to operate within certain pressure ranges, and the distribution pattern of a sprinkler can be altered dramatically with a change in operating pressure. A sprinkler specification sheet can provide information on the nozzle, plates, pressure and flow requirements for a specific sprinkler, along with a measure of its wetted footprint, or the area a sprinkler will wet or cover. This can help in determining the appropriate spacing for the sprinkler, as well as the required pipe sizes and pumping capacity. The layout of an overhead sprinkler irrigation system should be set out to industry best practice. To achieve best practice and obtain scheduling coefficients of less than 1.5, sprinklers should be arranged to ensure every container in an irrigation zone or grid receives water from 4 sprinklers. Older conventional system designs do not provide this sprinkler layout and deliver much higher scheduling coefficients, causing excess water use, increased watering time, nutrient leaching, uneven cropping, increased labour costs, and reduced production. Evaluation and maintenance are essential parts of operating an efficient and effective production nursery irrigation system. Even the best systems need regular measuring, evaluation and maintenance to provide satisfactory long-term performance. Many industry best management practice, or BMP, programs also require evidence of regular system evaluations to maintain performance. The following video shows how this assessment can be done. A system evaluation involves making visual observations along with measuring and recording pressure and discharge rates of sprinklers. These measurements can then be compared with industry best management practice parameters and with previous test record measurements. First, it is necessary to locate a pressure gauge or measuring point in the system to record the pressure at the irrigation zone or grid during the evaluation. Pressure measurements at the pump or the pump house do not always reflect the pressure available at the test area, but can be useful for comparison or future troubleshooting. A pressure gauge or measuring point is best located at the inlet to the irrigation zone or at a sprinkler head located within the irrigation zone being tested. A pressure gauge can be used directly, or alternatively a Schrader valve can be used. Next, it is necessary to select the area to be tested. An area with no plants in place, where the catch cans can be located, but representative of the irrigation zone, should be chosen. It is best to test an area as large as possible within the irrigation zone, and wherever feasible, include at least one outside edge of the zone to be tested. Growers sometimes are aware of underperforming areas within an irrigation zone and may wish to include those in the test. The system should be operated for a short period of time to ensure all components of the irrigation system are performing correctly. Be aware of correct system pressure, sprinkler blockages, filter pressure losses or backwashing, competing irrigation events, and other factors that may affect the result. Once the pre-check has been completed, reset the system. After checking the system, the catch cans are set out in grid formation in the selected test area. Catch cans should be evenly spaced with a maximum spacing of 1 metre between cans. Ensure that all catch cans are the same size, in good condition, set out level, evenly spaced, and not restricted from collecting water from the irrigation event. Weights can be placed in the catch cans to prevent them blowing over if prevailing wind is too strong. Map the irrigation zone indicating the test area, all sprinkler locations and the relative sprinkler and catch can locations. Measure and record catch can diameter, sprinkler type, nozzle size, plate, sprinkler height, layout spacing, number of laterals, sprinklers per lateral, total number of sprinklers. Once the area is set up, it is time to run the test. Operate the irrigation zone and record the duration of the irrigation. Record the pressure within the system during the test. Record details of wind direction and speed. At the conclusion of the irrigation test, measure the volume contained in each catch can. The field evaluation is now complete and the test area can be returned to normal operation. Remove any pressure gauges and any Schrader valves that were used during the evaluation and return the irrigation controller to normal operation. Now the collected field data can be entered into the Waterworks calculator to determine the system performance parameters. Data collected from each catch can evaluation can be recorded and used to benchmark the system, and in the future used to compare results to ensure continued system performance. Further information can be found in Nursery Industry Water Management, Best Practice Guidelines, and the publication Managing Water in Plant Nurseries, both available from the Nursery and Garden Industry Queensland. This short training video has been supported by South East Queensland Irrigation Futures, the Rural Water Use Efficiency Initiative, and Nursery and Garden Industry Queensland. Special thanks to Golden Grove Nursery, Bundaberg Regional Council Nursery, and Harvey Bay Nurseries.
Before you can schedule your irrigation on a daily basis, it's important to know how much water your plants are using at various stages of development. Plants of similar water use can then be grouped together under the same irrigation system. Each station can be given a percentage of the daily evapotranspiration rate to match plant water requirements depending on the plant type and growing environment. This information can be determined either by comparing plant water use to evapotranspiration, or it can be found by direct measurement of the potted plant. To find out how much water a plant requires each day, we need information on the daily evapotranspiration rate and the relative water usage of a range of plants as a percentage of potential evapotranspiration. One source of this information is automatic weather stations, which are now available and will calculate evapotranspiration and provide it on a daily basis. Another method of gathering evaporation data for irrigation scheduling is to install a Class A evaporation pan and read the previous day's evaporation first thing in the morning before setting the irrigation. This allows the operator to read the previous day's evaporation, estimate evapotranspiration and crop water use, and set the irrigation times accordingly. Evapotranspiration is specific to each nursery. A weather station or pan should be installed in a location under the same conditions as most of the nursery's growing areas. When using evapotranspiration data, a crop factor needs to be applied to account for the difference between evapotranspiration and the amount of water different plants and plants at different stages of development will require. Due to the huge variety of plants grown in the nursery industry, there is little or no published data on crop factors for nursery crops. For irrigation scheduling, initially assume plant water use is the same as evapotranspiration until crop factors for different plants, stages of growth, and growing environments can be generated through the calculation or measurement of crop factors. There's a method for calculating crop factors at the end of this presentation. Some simple measurements taken at different stages of plant development enable a nursery operator to reorganize where plants are in the nursery to better match applied water. and be informed on the amount of water each plant needs to maintain vigorous growth without overwatering and leaching fertilizer from the container. The most common method used is to weigh plants before and after irrigation. To measure water usage, select the container size and plant that is going to represent the irrigation frequency for each block. In this example, a 200 mm container. After the containers are at their maximum water holding capacity, or container capacity, weigh a representative sample of containers receiving the average application rate within the growing area. The average weight of the fully wet 200 mm containers in this example is 4,460 grams. Before the next irrigation, weigh the same containers to determine the water loss. In our example, 4,280 grams. Note that 1 litre of water equals 1 kilogram of weight, so measuring the volume of water lost can be easily calculated from the weight of the containers. The following table can then be used to work out how many millimetres of water have to be replaced. In the example, the water loss is 180 grams. The table shows in a 200 mm container, 30 grams of weight is lost for every 1 millimetre of water. This means that 6 millimetres of water has been lost. 180 grams of total weight lost divided by 30 grams per millimetre in a 200 mm container. The irrigation system in this example has a mean application rate of 9 millimetres per hour and a scheduling coefficient of 1.3 to water the driest container in the block. From this data, the runtime for the irrigation system can be calculated. The time to irrigate equals the millimetres to apply by 60 multiplied by the scheduling coefficient and divided by the mean application rate. The system would need to run for 52 minutes to replace 6 millimetres of water in the driest container. The high airfill porosity of growing media makes it difficult for moisture meters to be used in measuring moisture levels in growing media. However, soil moisture probes may be developed for measuring moisture contents over the ranges found in nursery production. An alternative method of setting the irrigation schedule using calculated evapotranspiration rates is to set the irrigation controller budgeting function to apply the required amount of water. To set the irrigation times, the controller can be programmed to apply 10 millimetres of water when set to 100%. On a cool, dull day, the evapotranspiration may only be 3 millimetres, so by adjusting this setting to 30%, all blocks will get the prescribed water. If it is a hot, dry day and the evapotranspiration is 10 millimetres, then this setting is adjusted to 100%. It is important that water applied stays in the container and is not leached through. By placing plastic bags under several containers, the volume of the water leaving the container, or leachate, can be measured. If the scheduling calculations are close, then very little water should run through the container, and the consequent volume of leachate should also be small. To determine how much of the applied water is retained by the growing media in the container, collect and measure the leached fraction. To collect leachate, before irrigation, on 3 containers in the area, place the bottom portion of each container in a heavy-duty plastic bag, secured with waterproof tape. These are the control containers or the reference plants for the area. Tape plastic bags on containers with other plants in them in the same area. At the end of the irrigation, check and measure the volume of leachate in each bag. If the control containers have significant leachate, then the application rate of the sprinklers or drippers is greater than the absorption rate of the growing media, and a more appropriate emitter should be selected. If some of the bags are empty, then they have been underwatered. Non-control bags containing significant volumes of water are being overwatered. This will produce excessive nutrient leaching and impact on plant growth. These plants should be moved to an irrigation block where the amount of water applied is more appropriate. If the application rate is too high, select a more appropriate emitter. If plants are over or underwatered, move them to an irrigation block more appropriate to their water requirements. The purpose of this next activity is to use weight rather than leachate to assess irrigation effectiveness and to fine-tune irrigation timing. Start with a number of containers that have been irrigated recently and are at or near their container capacity. Measure and record the weight of each of the containers and calculate an average weight to identify the target weight. When the next irrigation is due, weigh each container again. Average the weights and subtract that weight from the average container capacity weight. Based on the size of the container and the average water loss, determine the millimetres of water required to replace this weight. From the irrigation system mean application rate and scheduling coefficient, calculate the irrigation runtime necessary to replace the water lost in the driest container in the area. Then run the irrigation for the calculated time. After the irrigation is complete and drainage has occurred, remeasure the weight of the containers and see how close the weight has come to the container capacity. If the weight is well short, then the application rate is greater than the absorption rate of the growing media, and the system application rate needs to be slowed down by changing jet sizes or by pulse irrigation. Water being shed by foliage may also be a problem that needs to be considered. Crop factors show how much water the plant is using relative to the evapotranspiration rate. Crop factors can be used to fine-tune irrigation times using evapotranspiration data or to understand the relative water loss of crops by evapotranspiration. Crop factors differ between species and change as plants grow. A crop factor of 0.8 means the crop is using 80% of the water that is lost by evapotranspiration. The measured application and weather station evapotranspiration rate can be used to calculate the crop factor. In this example, if the evapotranspiration rate for the containers measured was 5 mm and the irrigation water applied was 6 mm, the crop factor is the irrigation water applied divided by the evapotranspiration rate, which is 1.2 in this example. Note that the crop factor will change as the crop grows, and these calculations should be done several times during the crop cycle to develop a full picture of the water requirements over the whole growing period. In this session, we investigated plant water use, the link between nutrient and water management, the variations in plant water use in different nursery environments, water held in growing media, scheduling irrigation systems to match water use, measuring plant water use, and measuring leachate volumes. The following video summarises irrigation scheduling in production nurseries.
The management of irrigation in a production nursery directly affects plant growth and profitability. Excessive irrigation can waste water, energy and labour, can leach nutrients and reduce growing media aeration. Insufficient irrigation can stress the crop, affect plant quality and reduce crop uniformity. Irrigation scheduling refers to how long, how often and when an irrigation system is operated to replenish the amount of water lost from a container since the last irrigation event. Effective irrigation scheduling has the following benefits. Monitoring and refining an irrigation schedule is one of the most cost-effective ways of improving water use efficiency. The following video contains information on the factors that affect irrigation scheduling and some methods that can be used to monitor it more effectively. An effective irrigation schedule identifies the optimum growing media moisture content, the amount of water to apply, and when to apply the irrigation. The characteristics of growing media affect the amount of water available to the plant. The volume of water retained in a growing media depends on the range of particle sizes. This also influences the amount of air held in the media. The higher the airfield porosity, the lower the water holding capacity. Plants draw water from the growing media and lose or transpire the majority of that water through the leaves in a process called evapotranspiration. The amount of evapotranspiration depends on the environmental conditions, plant type and stage of crop development, with the amount of water available governed by the growing media and irrigation scheduling practices. Plants in the open exposed to full sunlight and wind will use more water than plants under shade cloth, where solar radiation, temperature and wind are all reduced. Plants grown in polyhouses can experience higher temperatures and humidities, but are exposed to less solar radiation and wind. In summer, plants grown in polyhouses will generally use less water than plants outside. However, the opposite could be the case in winter or during wet weather. An efficient irrigation schedule is dependent on a well-maintained, efficient irrigation system with a uniform irrigation distribution. Nursery irrigation managers need to know how much water the irrigation system applies, as well as how quickly and how uniformly it is applied. A catch can test is the best way to determine this. There are a number of other factors that may need to be taken into account when deciding on an appropriate irrigation schedule. Irrigation scheduling can be accomplished manually, but is more effective when using an irrigation controller. Irrigation controllers can be an effective way of improving irrigation scheduling, provided they are programmed and managed properly. The budgeting or percentage function on an irrigation controller can be a convenient way to change run times over the whole production area. To identify the best irrigation schedule without overwatering while achieving an appropriate level of leaching requires an objective means of determining the amount of water to apply. Weighing containers and using data from an automatic weather station or using a Class A evaporation pan can assist with irrigation scheduling. Weighing a representative container from an irrigation block before and after irrigation can be used in conjunction with irrigation manager's skill and experience to schedule irrigation according to the current weather conditions. By measuring and recording the weights of a range of plants in various irrigation blocks, plants with similar water use can be grouped together. Measuring plant water requirements over the growing cycle and over a number of years will develop an understanding of the water requirements for the full range of plants grown. An automatic weather station can calculate the daily evapotranspiration, or ET, from the recorded weather data. Using the daily ET value, irrigation run times can be calculated using the mean application rate of the irrigation system. A less accurate alternative is to obtain daily evapotranspiration values from internet weather sites. A Class A evaporation pan is a simple method of obtaining reliable and consistent information on daily evaporation. The previous day's evaporation value can be used to calculate and set the irrigation volume for the day. A Class A evaporation pan has specific construction and location parameters. The evaporation data is normally measured daily at 9 a.m. To obtain accurate and consistent measurements, it is important that the readings and refilling of the pan occur regularly at this time. Further information on irrigation scheduling can be found in the publication Managing Water in Plant Nurseries, or for more detail refer to the nursery paper Scheduling Irrigation to Maximise Efficiency, August 2006. This video has been supported by the Queensland Government Department of Natural Resources and Mines under the Rural Water Use Efficiency Irrigation Futures Initiative. Special thanks go to the following businesses for their assistance in producing this video.
Here are some links to some other sources of information on irrigation. For further information, contact the Nursery and Garden Industry Queensland. This webinar was produced using funding from the Queensland Department of Natural Resources, Mines and Energy under the Farm Water Futures project.